or printed out. So I want to welcome everybody to Logic Control. My name is Ron Singleton, Professor Ron Singleton. Some of you I probably had for the circuits course. If you took the circuits course, maybe in the last 2 years, you may have had me. I recognize a couple of the names, but not everybody. So if this is our first time meeting, welcome. I'm sure we're going to have a fun and informative semester, and I look forward to doing that with you. I want to talk about a couple things. First, the syllabus. So again, if you have that out, I kind of want to, I'm not going to go through the whole syllabus, but I want to point out some things, and then if you have questions about it, you can ask me. The second page is important because the schedule for the semester is listed on the second page and how the class is going to be run. And then there's a couple items you'll need for the class that I'll talk about after I go through the syllabus. So if you have it out, please take that document out. And guys, at any time, you can open up your mic. If you have a question, you can open up your mic. I'm using Blackboard. I know UC switched over to Canvas, but I'm still using the Blackboard system. I know there's a couple apps out there. There's Zoom, WebEx, but this has been working for me for the last couple semesters. So I'm going to try this and see how it works out. I haven't really used this app for, I don't know how well it can share documents. We have, in this class, we have, I won't say a whole lot, but we have a fair number of PowerPoint presentations, and often what I do is I pre-record those. Sometimes I don't know how they're sharing real time, but we'll see how. I may try to do that. We'll see how this works with sharing documents. I didn't really do a lot of that. I think last time I taught the course, I just pre-recorded the PowerPoints, but I do want it to be a little bit more interactive, so I might try something different. But anyway, if you have the syllabus out, again, my name is Professor Ron Singleton. You can call me Ron. My email address on the syllabus, that's my personal email address. The reason I have that listed is I pretty much check that before anything. So I know you guys, if you want to use the UC system, you're welcome to email me there. It's just that I have that email address here because that's the one I'll see first. So if you want to email me through UC system, I'm okay with that. Just realize I might not get to it right away. If it's something that's urgent or you want to get to me, in a more timely fashion, then you can use the email address listed there. If you use the email address listed on the syllabus, you want to make sure you write UC student in the subject heading. And that way I have a filter set up. It'll go right into my UC folder. I'll click that and check it pretty much every day, and I'll get your message. Below that is a phone number. There's my office number, which the way I printed it out here is kind of grayed out. The best way to get a hold of me if you need to talk to me, and the quickest way is to text me. Now, if you look at the syllabus in red, I have a number there that you can text, and you can actually, it says text only, but you can actually leave a voicemail if you want to. Now, I don't have a cell phone, so what you have there is if you're familiar with Google Voice, this is a number that I give to students just for the purpose of texting, since I don't have a cell phone. So if you want the fastest, by far the quickest way to get a hold of me is to send a text to that number. You can text me anytime, day or night, I don't care, because if I'm asleep, I won't be looking at the computer at the text. You can also leave a voice message there, and I will get the voice message. So again, UC email is fine. My personal email is probably best. And then the quickest way to get in touch with me for any reason would be to send a number at the number I have listed there to text. The meeting day I have listed there, you guys know what that is. This web stuff, I don't really have office hours, but pretty much, guys, if you need, if we need to talk about anything or if something's not clear, I don't know if you have a class right after this one, but I'll be happy to leave the camera live. And after class, I can answer any questions if we need to do that. If that doesn't work for you, if you have a class right after this one, we can schedule a time. I'm going to leave it open kind of by appointment. I'm not going to set any office hours. So if we need to get together through the camera, we can do that. I don't have any problem doing that. And I don't know if you guys are on campus or if you're from home. I don't know what the school is doing now. But if you're here and we actually need to meet face-to-face, I also don't mind doing that if it requires that. Sometimes when we work with the program, If you get stuck on a PLC program, it might be easier just to kind of meet up somewhere. I do take care of my 80-year-old mother, and I don't want to bring any viruses home to her. So if we do meet face to face, as long as we, we're masked up and maintain social distancing, I don't mind doing that. So just keep that in mind. Now, the textbook. There used to be, I've been teaching this course since 1999. And all the way up until 2004, there was a textbook, but each year the textbook went up in price. And it just got to the point to where it was ridiculous. So around 2004, I did away with the textbook, and I basically spent a whole summer putting everything on PowerPoint. So there is no textbook for the course. However, there are two things you need to purchase. So there's no textbook. There's a lab manual, and then there's a simulation software that you need to purchase. Now, I used to order the lab manual to the UC bookstore, but then that started to go up in price. And so for the last maybe 3 years, well, we were meeting face to face, and I would, on the first day of class, I would ask the students if they wanted me to order the book, or if they just wanted to go to Amazon and just kind of get it and pay, a lot less money for it. And pretty much everybody just kind of went out on the web, found the book, and paid for it. And I think you save money doing it that way, buying it from Amazon or somewhere other than, instead of, I should say, using the bookstore. So what I'm saying is this: there's no textbook. There is a lab manual you'll need around the fifth week of class. You'll need to get a lab manual. So what I would recommend, what I'll do is I'll email or I'll post the ISBN number and a copy of the lab manual that you need to get. And what I would recommend is get that like kind of right away, only because if you have any kind of issues or trouble finding it, when we start the lab part of the course, I want to hit the ground running. You got to have the simulation software, and you got to have the lab manual. Now, the software is it's a software called Logic Pro, and what it is we used to actually meet. This was years ago when we were on the Victory Parkway campus. We actually have a lab. You guys may have been over to the lab over at the Victory Parkway. We have a PLC lab there. We used to actually do these circuits with actual machines, but since COVID and a lot of things happened with the school, the College of Applied Science and Engineering combined, and so things changed. So we kind of moved this to simulation software. So we won't be using the actual hard machine PLC. We'll use simulation software called Logic Pro, and that's the other thing you have to purchase. Now, last time I checked, it was around 35 or 40 bucks. So I don't know if you can get a lab manual for 20 bucks and the software, we'll just say worst case 40 bucks. You should be out of no more than 60 bucks. Both the software and the lab manual, again, you don't need that until the 5th week. However, I would recommend getting that as soon as possible. The other thing is, since I did away with the book, I moved everything to PowerPoint. Usually what I recommend for students is that you get a 3-ring binder and a 3-hole punch. And that way, the PowerPoints are up on Canvas. You can download those. I highly recommend 3-hole punching those. And just as we talk about them, put all those documents in your 3-ring binder. Normally, if we were meeting face to face, what I would do is I would come in, I would make UC pay for it. I'd print out all the documents and hand it out in class. I wouldn't even make you print them out. But because of the social distancing and the online class, I highly recommend that you just, as I post them, you print them out, put them in the 3-ring binder, and what you'll end up with, number one, is a textbook. And the second thing you'll end up with is a method to study for your exams and programs. You'll have everything right there in order. So 3-ring binder, 3-hole punch, and then you'll be in good shape. I'll say more about the software. The other thing I want to mention, when you be careful when you buy the lab manual. The author that wrote the lab manual actually has 3 books. He has a textbook, there's a lab manual, and there's an activity manual. And the covers look exactly alike. So I've had students in the past, they thought they were buying the lab manual, and in reality they bought the activities manual, and you can't use that. So when you decide to purchase the lab manual, make sure it says lab manual on it. And again, what I'm going to do, I'll take a picture of the cover, and I'll give you the ISBN number, and I'll post that, and then you can see what you need to buy. And I forget the edition of it, but pretty much those additions from one to the other, they didn't really change a whole lot. But we'll cross that bridge when we get to it. Okay, so grading. So this is probably what's important for you. So if you look, if you have the syllabus in front of you, the categories, we have quizzes. I'll have homework. Pretty much every week you'll have a homework assignment. There's 4 exams, and then there's labs. So quizzes, I'll give you every week there'll be a quiz, a time quiz. Now the one I give you this week, probably won't be timed, but all the other ones will be timed. You'll have 12 minutes to do the quiz. I'll have those set up for Fridays at 9:05. So at 9:05 you'll log onto your computer, you'll take the quiz, you'll have 12 minutes, and at that point I think the system shuts down. Now, last summer when I taught, it was one of the guys was saying, well, I need more than 12 minutes. You really, you don't have time to sit around trying to figure problems out. You really got to know the answers, because you got there's usually 10 questions. So if you got to search through, if you're not studying and you're trying to search through your 3-ring binder to find the answer, it's going to time out on you. You actually have to know the material. So I think 12 minutes for 10 questions, and some of the questions are stupid easy. Some you got to think about a little bit, but I think 12 minutes should be fair. We'll see how it works out, but that's how I plan to set it up. 12 minutes, and again, the one this Friday, I'm pretty sure it won't be a time one, but after that, every Friday you'll have a time quiz. So there's quizzes. Now the quizzes, since I don't do makeups at all. And so what I'll do is I'll drop the 2 lowest grades for quizzes. I won't drop anything else but just quizzes. I won't drop any exam grades or homework, just the quizzes. I'll drop the 2 lowest grades at the end. And the reason I'm doing that is because people get sick, and we got COVID, we got a lot of things going on. So rather than me try to make makeup quizzes, I'll just drop the 2 lowest quizzes, and then we don't have to worry about trying to make anything up. Homework. 4 exams, the weights are there. I won't do any adjusting or dropping of exams or homeworks. Homework, I pretty much want every week. Sometimes what I'll do, if it's something that you upload to me, I'll have it set to where the link expires. So I kind of want it that way to keep you guys on schedule. But if you get into some trouble, let me know, and I'll be a little bit flexible with that, but not a whole lot flexible. Exams are important. There'll be 4 exams. At least one of those exams, possibly more, but at least one of those exams will take the form of a program. Typically what I do is give you 2 written exams, a program, and then a project that I count as an exam. But we'll see how that goes through the semester. I'll think about that some more, and that's the way I've done it in the past. So the rest of this you can just you can read yourself, and if you have questions over the grading, I grade on a 10-point scale. So if you have any questions, you can ask me about that. There says a prerequisite, the circuits analysis 1 course, this DC circuits. If you had that, it will be very, very helpful. However, if you didn't take that course, you don't have to drop this course. You'll be fine. There are a few things that I bring from circuit analysis into this class, but you'll be able to get through it even if you didn't have that prerequisite. And then on the rest of the first page of the syllabus is the course objective, which I'll let you read that yourself. And there's a list there of topics for course content. Pretty much over the years, I think I've gotten through at least 90–95% of that. So these are the topics you can expect to go through and to understand. So some of you look at that, it may make sense to you. You may be familiar with it. Some of you may have already had experience with PLCs or logic control devices, so some of this might be familiar. But pretty much that's what we'll go over, and I guarantee that everybody in the class will take something away and you'll learn something. Let's look at the second page of the syllabus. Now this is important because this is the schedule. If you notice, if you have that out in front of you, it's color coded. You have what I call blue weeks and you have red weeks. The blue weeks, the way it's listed, week 1 through 5 and week 11 through 14. The blue weeks are weeks that will actually meet through camera on web. The red weeks, week 6 through 10, those weeks, week 6 through 10, we'll meet, but we won't meet on Mondays and we won't meet on Wednesdays. What we'll do is we'll meet on Fridays, and those are typically will be the days when we get to the lab portion of the class, will be the days that you upload, that you submit your lab assignments. So the way it works is like this. We'll spend 5 weeks going over basically the introduction, which will kind of start today. We'll talk about PLC hardware. We'll talk about numbering systems. We'll talk about things that are important to understanding how to program. And then towards the end of that 5th week period, we'll get into just some basic programming. But then we'll get into the lab. And at that point, for 5 weeks of lab, you'll have time to go, and you'll use, in theory, what you do. And I don't know if students actually do this. In theory, you'll use the Monday, Wednesday time, this hour, to work on your assignments. You should be able to get most of it done in the 2 hours that I give you for Monday and for Wednesday. And then on Friday, we'll meet. Now, sometimes on Friday, I'll lecture. Depends on what the material is. Sometimes I'll just check in with you to make sure everything's, kosher, everything's good. If you have any questions, and we may not lecture. Sometimes, depending on the material, I might pre-record the lecture. There's a heavy PowerPoint or something, I might pre-record that and have you watch the video before we meet on Friday, and then we'll talk about it. So it just depends. But the scheme is, the big scheme is, first 5 weeks, we're meeting Monday, Wednesday, Friday by camera. The next 5 weeks, the lab weeks, we'll meet only on Friday. And Monday, Wednesday, in theory, you're doing lab work. And then the last 2 weeks of the semester, we'll go back to meeting, on camera. And then every Friday, regardless of whether it's a lab week or not, there'll be that quiz that I talked about. Okay, so make sure you read that. It's important that you understand that. And at the very bottom of this, I think there's one holiday, Martin Luther King Day. I don't know if that's an official holiday, but it is for me. So if it isn't, I'm making it one. And then there's the reading day. I don't know how I did that last time, but if there may be a pre-recorded lecture. We'll see how that works out. And then the final exam I have set for the last day of class. Typically, we finish this course earlier than the other courses. And so if we do, I might move that final exam date, but I'll run it past you guys, and the majority kind of rules kind of thing. And if we need to keep it on the last day of class, we can do that. If we need to move it, we can do it that way. So we'll see how that works out. Now, I want to get into some course material because I got a few minutes. Well, I got more than a few minutes, but let me pause for a second and let me ask you, does anybody have any questions for me over the syllabus or any general things that I need to talk about before I start? Any questions for me? Now, if you see me look over here, it looks kind of weird. I'm looking into the camera now, but my computer's over there. So sometimes you guys can send me those messages and they'll pop up in a bubble. So I'll look over there away from the screen to see if anybody's done that. And nobody's done that. So I'm assuming you have no questions. So here's what I want to do. I want to talk about what is this class about? The name of the class is Logic Control. What does that mean, Logic Control? Why is it called Logic Control? And kind of what is the class about? So I want to get into that. Now, before we do that, I want to take attendance, and the way I'm going to do that is I'm going to have you guys text me. So take out your device, your cell phone, and I'll do this probably for the first couple of days or maybe the first couple of weeks. Just send me. I want you to send me a text at that number on the syllabus, and in the text, just put Logic Control Student. So I'm going to put the number on the board. I don't know if you can see it right here, but it's 513-494-6162. Let's see, I think that's in the camera. I can't see the camera on my screen, but it's 513-494-6162. So what I want you to do is right now, I'm going to pause for a minute. Go ahead and text that number. Text me at that number, and in the text, write Logic Control Student, and I'm going to use that for attendance. So I'll give you a minute to do that, and then we'll go ahead and talk about a few of this logic control topics. So 513-494-6162. Text me right now, and put Logic Control Student in the text. Okay, and then while you're doing that, at any point, guys, if you have any questions, you can just interrupt me, and I'll stop and clarify anything when I'm lecturing. And then right now, I see these little icons on the screen, so I really hate. I like being face to face, but I realize we can't do that. So I never get to know my students. I never get to see you. So you don't have to do this, but I do appreciate it sometimes if you guys turn your camera on. If you're asking a question, you don't have to, but if you turn your camera on so I can see who I'm talking to. Now I know some of you you might look a hot mess in the morning. You might not have your hair done if you're a female, or maybe you're a guy, you're sitting around your body. I don't want to see any of that. But if you don't mind, sometimes I would like you guys. So I know I'm talking to real. Okay, great. I got one person that's brave enough to have the camera on. I don't know who is that. The name disappeared. That's AJ. All right, AJ, thank you. Boom. That's a nice room too, AJ. I like that in the back.
Thank you.
All right. Let's get into a couple things. We won't do a whole lot today, but I want to just kind of give you a brief introduction. So let's talk about some things. So let's talk about, first of all, let's talk about the name of the course, logic control. First of all, what are we controlling? And then what does it mean, logic control? We use logic to control something. So what we're controlling is some type of machine, some kind of device. It could be a single device, like maybe a garage door opener, a motor, or it might be a whole factory, like a automobile plant, General Motors, Ford, Chrysler. It could be a whole factory. So it can be, this control thing can be as small as a simple motor on a garage door, or as large as a whole factory like General Motors or Toyota. The logic's the same. It's the same thing. So the term logic, what we mean by that is this. I don't know how well this shows up in the camera, but what I have written here, and as I go, guys, please take notes. Please take notes. I forgot. I am recording this, so if you need, what I'll do is I'll record the lectures, and then it may not be the same day, but within a couple of days of recording the lectures, then if you go to the class website, at the very bottom of the home page, there's a little blue link that says past lectures. So please show up to the lecture. Don't use that link as an excuse not to get up out of bed and say, you know what, I'm just going to watch the record. You want to come to the lecture because you want to ask questions and just kind of interact with me and with the class. But if for some reason you do miss a lecture, or if for some reason you need to go back and review it, there's a link at the bottom of the home page that says past lectures. You'll be able to click that link and you'll be able to bring the recording up, and the lecture will be there. So I want to just mention that. So logic, getting a certain output based on a set of, and this is important, predefined inputs. Now normally when I give that definition, I say getting a certain output condition based on a set of predefined input conditions. And so this ideal, these are electrical terms, outputs and inputs. I want to talk about what do we mean by an output and an input. Well, typically an input is a signal that comes from something called a switch or a sensor. In this class, we deal with switches and sensors. And I want to talk about the difference between the two. And then the output, what is an output? Well, an output is some device that you want to control. It might be something as simple as a light bulb. It might be, in the case of the garage door opener, a motor. It could be, there's a whole lot of things that you might want to control based on a certain number or combination of input conditions. So that's kind of what we're dealing with. So the logic part of it, and then the control part. What does it mean to control something? Well, in the simplest way to think about it, if I want to control anything, I can turn something on. Let's say a light bulb. I can turn the light bulb on. I can turn a motor on. I can turn a device on, or I can turn the device off. So by control, what I mean is I have some machine or some device or some process or system. I can turn it on, I can turn it off, I can speed it up, I can slow it down, etc., etc., etc. I can do these things based on certain output conditions. So I want to show you what I mean by that. The simplest control circuit you can have. I want to show you what I mean by that. What do I mean by logic and using logic to control a device. So let's look at the world's simplest control circuit. The world's simplest control circuit. Let me show you what that looks like. So here's the world's simplest control circuit. Now, if you have circuit analysis, you'll recognize this as a power source, a battery. So here's a battery. Now, I'm assuming you guys have had the circuit course, so at any point, if any of the symbols that I put on the board are not clear, please interrupt me and ask me about it. But I have a power source, battery. And then this thing right here is a switch. And then over here is a light bulb. So this simple control circuit, all it's going to do is turn the light bulb on or off. So this right here, the switch, this is what I mean by input. Now really what the input is, what it's going to turn out to be in this class, is a signal. If you have an input, there's going to be the presence of a signal. If you don't have an input, it's going to be the absence of a signal. But for right now, what I want you to think about is switches. When I'm talking about inputs, I'm just talking about switches. And you know what a switch is because you use them all the time, right? I actually should spend some time talking about that. Let's talk about that. So we have switches, we have buttons, and we have sensors. Now, if you guys can open your mic, I'm going to ask some questions here. We have switches, we have buttons, and we have sensors. So I'll tell you what a sensor is in a second. But what's the difference between a switch and a button? Can anybody answer that? What's the difference between a switch and a button?
A switch is basically, it has an on and an off position to complete and leave the circuit open, whereas a button is once you press it, it closes the circuit and is always left open, not pressed.
Exactly right. Perfect answer. So here's what he said. So if you have a switch, here's a switch, right? Now let's examine this switch a little closer. I don't know what I want to do. Hopefully you can see. I don't know if you can see right. I'll just erase it. So this switch. So make sure you're writing this down because this is what I might ask you about. I may ask you about on this first quiz. I don't know. I haven't really thought about it. But here's the switch. So the switch, this part right here, this switch, that's like a light switch, right? And so what happens when you come in, let's say you go into your bedroom and you move that little lever up, you move it up and down, you move it one way, the light comes on, you move it the other way, the light goes off, right? So that's this part, that represents the part that moves. So if I want to turn something off, then this right here is the brake, that switch is open. If I want to turn something on, I'll push a lever down, I'll move some mechanical device, and what ends up happening is this switch is closed. So current cannot flow through this circuit because there's an open here, but current can flow through here because the switch is closed. It made contact. There's a path for current to flow. The thing that you're moving though, when you turn your bedroom light switch off or on, the thing that actually moves, the mechanical device that moves, is called a pole. P-O-L-E. So make sure you're writing this down. The thing that you move when you move a mechanical switch is called a pole, P-O-L-E. And the thing that you connect to when you move the pole, the part over here, is called a contact. This little represents the contact. And that's the part of the switch that the pole touches when you close it. Or is a part of the switch that the pole goes away from when you open it. Now, there's this term called the throw, like you throw a baseball, the throw. The throw of the switch is the number of ways you can move the pole to touch a contact. Let me say that a second time. The throw, like you throw a baseball, the throw of a switch is the number of ways you can move the poles to touch a contact. So, I have a pole here, a single pole. I have one pole here, and I can only move that pole one way to touch the contact, and then it looks like this. And so one of the things you got to be able to do in this class is to name a switch based on what I just described. And here's what I mean. Since I have one pole here, I would call this a single pole. And since there's only one way to move the pole to touch a contact, I say that's a single throw. This right here, the way I have it drawn, this switch is a single pole, single throw switch. You got to be able to name a switch like that. What if I do this though? What if I have something like this? What if I have a contact over here, a contact over there, and I got the pole like that? So now what I can do, you can see my pen. Now what I can do is I can take that lever and I can move it that way and touch that contact, or I can switch it the other way. Now you might call that a two-position switch. That's kind of what it is. But technically the way you would name that is, I have a single pole. So I have a single pole. But now I can throw the pole. I can move the poles in two different positions to touch a contact. I can move it to the left. I can move it to the right. So this is a single pole double throw. If you were going to buy this switch, you would ask for an SPDT. The first one would ask for an SPST. Single pole, single throw, single pole, double throw. And it gets more, there's a lot of different ways I can do this. For example, I can have something like this, where I have, let me do this a little differently. So I might have something like this. I might have a pole here like that. And then what they usually do is put a little dotted line down between these two. So now what I have here is I have two poles, and this dotted line means that when I move one, they both move together like this. They're in sync. When you move the lever, both of those poles move. So now if I name that, what do I have? I have a double pole, but there's only one way I can move those poles to touch a contact, so it would be single throw. So that kind of thing. You can probably look this up on YouTube or something. You got to be able to name switches. Okay, so we got various types of switches. Now here's the simplest switches I can use in the control circuit. Let's talk about a button. So I don't know who that might have been AJ that answered the question, but a button is something that you press, right? A switch is something that you throw or you move. A button you press. So you're familiar with buttons, like maybe a doorbell. You go and you push the doorbell. So the way that works is, think about a doorbell. So a doorbell, the way I draw that is I actually have two contacts like this. Here are my wires. And then the pole, instead of having a metal, that metal metallic pole, instead of having something like, you have a pole, but it's like this. And then you got some kind of connection point to where I can press that down. So when I press that and close the switch, then it looks like this. So now my button is closed. Here's an open button, and here's a closed button. So current cannot flow through the first one. It can flow through the second one as long as I have it pushed. So what they have here in the side of the button is they have a spring, a little spring, and that spring is set in there in such a way that it has an upward force on the pole. And so that spring is keeping the pole and the contacts from touching each other. There's an upward force on it. And what you got to do if you want to make contact, the pole and the pole and the contacts, you got to press it down. And then it looks like this. So now you're pressing this. This is the way a doorbell works. As long as you have the doorbell pressed, then the pole is making contact with the contacts, and the doorbell is going to ring. But when you release it, that spring pushes the pole away from the contacts, and then the doorbell stops ringing. So you've all experienced that before. Any button works like that. Now, here's what's important. The ideal, and this is really important for this class, a button A button can either be normally open or normally closed. Write that down. A button can either be normally open or normally closed. Now, what does it mean to have a normally open device, a normally open switch? Well, here's what it means. If it's normally open, the doorbell is normally open because if you take the switch, if you lay it down on the table, there's no human interacting with the switch at all. In this normal state, the contacts are open. And so what you would do is you would name this. This is a normally open push button. So in this class, I will say NOVP, NOPB, right? Normally open push button, a doorbell. Well, if I wanted to, what if I did this? What if I rearranged the switch so that my contacts are here, but now my pole is right there, and then the part that I push comes up like that. And I still got the spring in there, but the spring is under here, pushing up on that pole, and it's forcing that to maintain contact. So here's another type of button that's always closed, as long as you're not pressing it. The button would be like the button on your car door that turns your inside light off and on, or on your refrigerator. You know there's a button on your refrigerator. If you open the door, if you press that button, you press the button with your finger, then you actually turn it off. But when that button is just sitting on the table, you're not interacting with it at all, in its normal state, that switch is closed. So the way you would name this button, I'm saying switch, I mean button, the way you would name this button, in this case, it would be a normally closed push button. So the idea in this class of something being normally open and normally closed, that idea, that concept of being normally open and normally closed is really, really important for this class. So make sure you, all it means is the state of the switch or button or device when there's nobody interacting with it. If the pole and the contacts, if they're closed, then we say that the device is normally closed. If the pole and contacts, if they're not together, we say that the device or switch is normally open. So the idea of something being normally open and normally closed is important. Any questions over that before I move on? We got switches, we got various different kinds of switches that we name. We got buttons. A button is something that you can press. It can be normally open or normally closed. And then we got sensors. Well, what is a sensor? A sensor. Well, a sensor, what it really is a type of transducer. Let me write that down. A transducer. What is a transducer? A transducer is any device that converts energy from one form to another. Write that down. A transducer. It's just a fancy name for a sensor. A transducer is any device that converts energy from one form to another. So, for example, let's see, a light bulb is a transducer because it converts electrical energy to light energy. A speaker is a transducer because it converts electrical energy to mechanical or acoustical energy. There's many, many types of transducers that we deal with every day. Well, in this class, we use transducers to convert one physical quantity to another. Typically, the thing that we want to convert a physical quantity to is a current or voltage. And the reason I want to convert it to a current or voltage is because usually what I want to do is take that physical quantity and feed it to a machine or some device for the purpose of control. So for example, perfect example, a thermostat. How's a thermostat work? A thermostat has a sensor, a transducer that converts the physical quantity of temperature to a voltage or to a current. And depending on the level or the magnitude or amplitude of that voltage or current, I can get the furnace to turn on, turn off, whatever I want to do. So we got buttons, we got switches, and then we got sensors or transducers. And you'll get familiar with a lot of these things that I'm talking about as we go through the class. So I spent a lot of time talking about that. Anybody have any questions over switches, buttons, or transducers? Any questions or comments? Okay, before I run out of time, 'cause I think What is this class over at 10? I got like, let me finish this because I want to get through a certain part today. So the whole class, everything we do is based on logic. Let me write this down. So logic. So there's three fundamental logic definitions. There is and logic, there is or logic, and there is not logic. And now that we talked about switches and buttons, we can get into what that means. So basically, this logic allows us to control the machine based on certain conditions or certain situations. So back to this circuit. This is the simplest control circuit I can have. I have a single pole, single throw switch, and I got a light bulb. So if I want to control the light bulb, I can close the switch, the light bulb will turn on. I can open the switch, the light bulb will go off. This is the simplest control circuit you can have. But here's what I want to do. If this switch right here, if it's open, if that switch is open, we're going to say that that input condition is false. I'm going to use the letter F for false. If that switch is closed, we're going to say that that input condition is true. I'm going to use the letter T. I'm not going to write the word out. So if the switch is open, the condition of the switch is false, or the condition of the input is false. If the switch is closed, the condition of the input is true. And then the light bulb. If this light bulb is off, then we're going to say that the state of the bulb or the output is false. If the light bulb or device is on, we're going to say the state of the device or is true. And if I do it that way, then what I can do is I can make this table. Now this table is really, really important. I can make a table. What I do, I put inputs on one side of the table and output over on the other side. So my input, I want to put the state of the input. What the input for this circuit, the switch can either be open or closed. So the input, if it's open, I say the input condition is false. If it's closed, I say the input condition is true. Now, based on whether that switch is open or closed, my output condition is if my switch is open, false, then my output is going to be false. If my switch is closed, the bulb's going to come on, my output's going to be true. This right here is called a truth table. Truth table. And this truth table defines the type of logic we're going to use for a certain application. Now, think about this. What if I add another switch to this circuit? Watch this. If I add another switch to this circuit, so instead of having a single pole, single throw switch, I do something like this. I got this switch, and I got that switch. And I'm going to call this switch A, and switch B. Now we're getting into something here, because now what we can do is we can control this motor, light bulb, whatever this is, based on a certain combination of conditions that we might want to happen or not to happen. So what I'm saying is, if we look at the truth table for this, what would that look like? Well, the first thing we got to do is get all the possible combination of switches. They can both be open. One can close, other can open, vice versa. We got to get all the possible combination of inputs. So I'm going to make that table. Here's switch A, here's switch B, and for my light bulb, we'll just call this X. So we'll call this X. And usually what you do is you put this line down here to separate the inputs from the outputs. Now I got to get all possible combinations of the switches, so let me do that. All right, so both switches can be open like they are right now. That's this condition. Maybe I close B and open A, or maybe I'll close A and open B, or maybe I have them both closed. no matter what I have though, if you look at this circuit, and what's the only state of switch A and B that will allow me to turn the light bulb on? What's the state of switch A and B that will allow me to have an output? Well, the only way I can have this light bulb on, since there's a single path through which current can flow, is right here, where both switch A and B are closed. If both switch A and B are closed, then the light bulb will light. If I open just one of those switches, I don't get any power to the light bulb. So for all these possible combinations, I don't get an output. Only for the condition where both switch A and switch B are closed do I get an output. So this is called AND logic. What we've done here, guys, is we use an electrical circuit to make a basic decision for us using AND logic. So an example of this would be if you when you get in your car and you stick your key in the ignition, if you still have a car that uses the ignition key, you stick your key in the ignition and you have your door open at the same time. What happens? Well, that little bell, ding, 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 it's a warning bell or buzzer. It warns you that your door is still open. So what they have is they have a switch, a little tiny micro switch in your ignition system, your ignition where you put the key, and they have another one on the door that turns the interior light off and on. If the ignition switch is closed and the door switch is closed, ring a buzzer. You've used this AND logic to make a basic decision. AND logic, the only time I get an output are when both or all input conditions are true. Well, what if I do this? What if I rearrange this to where I have switch A and B? Now before, if you remember from your circuits course, those switches were hooked in series in the end. What if I hook them up like this? So now I got switch A here and B here. What if I hook them up in parallel? This is the first connection with series. This is parallel. So if you think about this, well, let me for my truth table now. Let me get rid of this. If both switches are open, nothing happens. The light bulb will not light up, so my output is going to be false. But if I close switch A and leave B open, current can flow through A. Or if I leave A open and close B, current can flow through B. So if either A or B is true, there's a path for current to flow. So if either A or B is true, I get the light bulb on here, I get the light bulb on here, and of course, if both of these are closed, I get the light bulb on. So I get an output if either A or B is closed, or both of those switches are closed. This kind of logic is OR logic. So if I want to control some kind of situation where if I get an input or another input or a true, I can make a decision based on this chart right here, this truth table. So we have AND logic, we have OR logic, and then the last thing I want to show you here for this two things, not logic. And the way we represent, I'm not going to really draw a circuit for it, but not logic is just using a normally, if I use a normally open push button, if this button is, so if I get rid of this, and put that push button right here. So if that button is not pressed, then the light bulb is off. If the button is pressed, then the light bulb is on. So this is a little bit harder to wrap your mind around, but we use this to represent not, and we'll get back to that later at another time. The truth table for not logic, false, true. So here's my input, and here's my output. So if this is false, this is true. If this is true, this is false. And so I'll say more about this later. I don't want to get tied up into this because I got like 4 minutes. There's one more thing I want to show you I'm going to kind of rush through this. I apologize. Actually, you know what I'll do? I'm going to take my time and go through it. And if I go over and you guys have a class and have to sign off, just watch this at the end of the, you can go back and bring the video up and you can watch it. Because I kind of want to take my time for this last part. I got one more thing I want to talk about. So if you have to sign off, I understand. Just watch the video for this last part of it. Because we looked at, in detail, we looked at AND logic, we looked at OR logic, and I just kind of briefly put up there a normally open push button to represent NOT logic. This allows us to make decisions. If you have a garage door opener, you guys know if the garage door is coming down, let's say this actually happened, I have a pit bull at home, and my garage door was coming down, and she walked through the garage, and the door stopped. There was a sensor on the door to stop it. So if that sensor is true, and it's true that the motor is running, stop the motor if there's something in the path of the sensor. There's a lot of different ways you can use this stuff, I'm sure you can imagine. But here's the thing. In every case I showed you today, when I showed you AND logic and I showed you OR logic, it required human interaction. A person had to open or close the switch. I want to talk to you briefly about something called a relay. And before you guys sign off, there is a homework assignment. Make sure you read that. I want to say it's due Monday, but make sure you read that, find out the due date, and it's just some research you got to do for me. So look that up, and they may talk about relays in there a little bit. But anyway, it would be nice if we can control those switches without having to be there. In other words, if I can have some kind of computer or some kind of application control those switches for me, the AND logic, NOT logic, so forth, I can have that all done automatically. So there's a device called a relay. I just want to talk briefly about how it's constructed, and then there's a picture of it on the class website. There's this picture of a relay. You can kind of see how it works. But anyway, let me just go through that briefly. What a relay is this. You may be familiar somewhere along the line, maybe in 3rd or 4th, 5th, 6th grade, you might have made something called an electromagnet. If you've ever taken like a nail, you can take a nail, you can wrap wire around that nail and hook that up to a battery. When you close that switch, then that nail becomes a magnet. If you open the switch, the magnetism disappears. So I can close the switch and I can use this nail to pick up paper clips. If I open the switch, the paper clips will fall off. That's called an electromagnet. Now, if you haven't seen that before, at some point go to YouTube, put in simple or basic electromagnet, and you'll see how this works. The thing is, though, what they do is they take a metal core, like a metal bar, and then they wrap a whole bunch of wire around this. So I got this wire. Now the thing about the wire is the resistance of the wire is directly related to how long the wire is. If you had the circuits course, you know resistance is the opposition to current flow. So the higher the resistance, the less current I have. The lower the resistance, the more current I have. So another way of saying that is the longer the wire, the higher the resistance, the lower the current's going to be. Now that's important because if you remember Ohm's law, if you had the circuits course, if I have a high resistance, I have a low current. And that's kind of what I want. I want a low current. So what I'm going to do is make an electromagnet. I'm going to wrap wire around a piece of metal. I'm going to use a lot of wire. So that when I hook this battery up to this electromagnet, there's just a small amount of current flowing through the electromagnet, but I still have magnetism that I can control. If I close the switch, I have magnetism. If I open the switch, the magnetism goes away. So imagine that now I have a single pole switch. I got this switch, and usually there's a spring, a really, really light spring pulling up on this. So I got this switch. And then what I'm going to do is take this electromagnet, I'm going to put it right below that switch. So I got my electromagnet right here. Here's the bar. And then I got my wires wrapping around it like this. Come out here to my battery. So I hope you can see that in the camera. But here's how this works. If I close this switch, I get current in the electromagnet, I get a magnetic field, and that magnetic field will pull this switch down. If I open this switch, the magnetism disappears, and that switch is going to be opened up by that spring. The thing is this, here's what's important. Since I have a lot of wire I'm using to make this electromagnet, this is a low current circuit. I may have milliamps here of current, thousands of an amp. This circuit here, that switch can be as big as I want it to be. So I can have this switch and wire so heavy that it might control 100 amps. Maybe I have 100 amps of current here in this circuit, and maybe 0.1 milliamps in this circuit. So I'm using a low current circuit to control a high current circuit. You still got to close the switch though, but I don't have to physically be there. I can connect this to a computer or some device so when I get current here, and I can have this switch open or close automatically. Now, I kind of rushed through this and I apologize for that, but really the way this is done, I showed you today basic and logic or logic and not logic, but the way it used to be done is not using physical switches. Well, sometimes you did, but mainly using this thing called a relay. So I'm out of time now. I went over by 5 minutes. So what I'm going to do is I'm probably going to say a little bit more about this in the next class. Anybody have any questions for me or comments? Okay, well, when you guys do your research, he'll talk about relays. And again, I'll say a little bit more about this because it's actually kind of, relays are not so much used now for logic purposes. In the old way of doing it, we use a lot of relays. But it really helps to understand what the software and the computer's doing if you understand relay logic. So relay logic is what we're talking about. Instead of using switches, we're using relays. That way we can allow currents to control our logic circuit. So if nobody has any questions, I appreciate you guys for sticking in there with me. I apologize for going over. Anybody have any questions or comments for me? All right, and AJ, again, thank you for opening up your camera. I at least know what one of you look like. I'm gonna get the rest of you to open up your camera at some point. So you guys have a great rest of the day. I will see you on Wednesday, and please, please, please stay safe.